Welcome back to electronics. This is Dr. Ferry. In this lesson, we will do a review of frequency response plots, including bode plots. In our last lesson, we did a review of transfer functions. Well, we need transfer functions for us to be able to do a frequency response. So this lesson, we'll define the frequency response for a transfer function. Actually, I'm going to go ahead and define it right here because this is all I really wanted to say for it. A frequency response is a magnitude plot of taking the transfer function h of omega. We want to take the magnitude of h versus omega, plot it that way, and the angle is the angle of h versus omega. H is a complex variable. And then we want to show the linear plots and bode plots corresponding to the frequency response. Let's look at a particular circuit. This is an RC circuit that we've looked at a couple of times in the impedance lesson as well as in the transfer function lesson. We found that the transfer function is equal to this h right here. And what we want to define is the magnitude and the angle. Well, let's take a step back and think about a magnitude of a complex number, a plus jb. The magnitude of 1 over a plus jb is going to be 1 over the square root of the real part squared, which is a squared, plus the imaginary part squared, which is b squared. So in this particular case, b is equal to rc omega. That is what multiplies j, and I've got that squared. And then the real number in the denominator is 1, so that's squared right there. So the magnitude is this. Now the angle, 1 over a plus jb, rather the angle of that is minus arctan, and the minus sign comes because this is the complex number is actually in the denominator. And then it's the imaginary part over the real part. So in this case, it's b over a. And a is equal to 1, and b is equal to rc omega. If I want to plot this, what I'm plotting on the magnitude is h of omega and then this magnitude. So I'm plotting this function right here. And it's a function of omega. One thing you can see is that as omega gets very large, this gets small. And then this is the angle, is the arctangent of rc times omega. And in this case, as omega gets large, this approaches minus 90 degrees. And as omega is equal to 0, it's 0 degrees. What's it mean, the transfer function here? It's really how a circuit processes signals of different frequencies. So in this case, suppose I've got an input that is a sum of two sine waves. And the sum of two sine waves, I've got an amplitude of 1 and an amplitude of 1, but different frequencies, 50 and 800. You could see the 800 as being the high frequency here, and the 50 as being kind of the low frequency there. So I've got the summation of two frequencies, and one of them at 50. So what I do is go to this plot at 50. This is a plot of my frequency response. At 50, I look at this value here. That's about 0.95. And at 800, I look at the value there. That's at about 0.13. So my output amplitude is equal to the input amplitude times the corresponding h at that frequency, the corresponding magnitude. So 1 times 0.95 is right here. The input amplitude times h to give me that output amplitude. And remember, just to write it up here, the output amplitude is equal to the input amplitude times h at that frequency. That's what we're using. And the other thing is the output angle is equal to the input angle plus h at that frequency. Well, in these cases, I have no angle, so the input angle is 0. So looking at the course, trying to figure out what these angles are, at 50, that's about minus 20 degrees. So that's where I get the minus 20 degrees in there. And that at 800, that's at about minus 85 degrees. So that's where I get minus 85 degrees. So the transfer function tells us what the output amplitude is and what the output phase is. And what we see here is that this particular case, it rolls off as we get to high frequency. So that means that higher frequency part of this signal gets attenuated. And you can see it here. The high frequency is much smaller than it was before, whereas it's a lot more dominated by the low frequency than it was in this case. So it let the low frequency through without much change, and it attenuated the high frequency. And we can see that by seeing what happens to this plot here. What we've looked at so far was linear plots. I want to show you a bode plot, which is the same values, the same information, but this time on log scales. So looking at the magnitude, now the magnitude is actually written in decibels, and that's what the dB stands for, where I take 20 times the log of the magnitude. And I plot it versus frequency, either radians per second or hertz, on a log scale. So I'm going to define what a decade is. If I look at this value, it's a frequency and 10 times its frequency. That's a decade. So it's omega to 10 times omega. Or in terms of hertz, it's frequency in hertz to 10 times that frequency. And it doesn't matter, it doesn't have to be 10 and 100, it could be somewhere in between. That's also a decade right there. So it's that distance right there. And the angle, we're just plotting the angle on the frequency scale, not doing anything special to it. It's just on a log scale on the frequency part. So what's the difference in the looks of these, linear plot versus a bode plot? This is a linear plot and its corresponding bode plot. So at every point, so example right here, I would take 20 times the log of 1, and I get 0 dB, which is where I get over here. This is where this goes to 0 dB. Over here, I'm at 0.1, so 20 times the log of 0.1 is equal to minus 20 decibels, and that's where we get minus 20 decibels over here. So this is at 1,000 radians per second. This is 10 to the third 1,000 radians per second. And the angle is the same information. I'm just plotting on a log scale over here. The characteristics of a bode plot. At high frequency, this has a slope of minus 20 dB per decade. And this, what is plotted specifically here is this RC circuit, the transfer function of this RC circuit. And we can draw this at higher frequencies as being kind of an asymptotic line there. And where these two lines meet up, that's what we call the corner frequency. Omega 0 is the corner frequency. For this particular circuit, the point where they intersect is 1 over RC. Now what happens in the angle? It goes from 0 degrees to minus 90 degrees as you get higher in frequency. So this levels off at minus 90. So that's the characteristics of a first order circuit and what the bode plot looks like. This is an RLC circuit. It's a second order circuit, and there are two cases that we're going to look at. One is called overdamped, and the other is called underdamped. So this is a transfer function. We've seen this before, and at high frequency, I can figure out what this slope is. Because this is a second order circuit, I've got an L and a C. This is minus 40 dB per decade. And I can figure out what this corner frequency is by drawing these asymptotic lines right there. So that corner frequency down here is 1 over the square root of LC. That's the corner frequency. It's kind of where the plot changes. Now, the angle goes from 0 degrees to minus 180 degrees as we go from low frequency to high frequency. Now, in an underdamped case, we're doing the same transfer function, and we can come up with these same asymptotic curves and I still have the value omega 0, where omega 0 is equal to 1 over the square root of LC. What we found here is that we didn't have any dependence on R here. But as R gets small, as R decreases, we get a resonant peak. For large R, what we saw in our previous case was overdamped. There was no resonant peak. So this is the resonant frequency range, and this peak value is a resonant frequency at which that happens. Resonant frequency. And at that point, that means the output is greater than the input. Output amplitude is greater than the input amplitude. In resonance, in the resonance region. In terms of, and the smaller R is, the higher the peak. The only difference with it, as R gets smaller, this becomes sharper in terms of the phase transition, sharper transition. And again, we're going from 0 degrees to minus 180 degrees on the angle. So that's the underdamped case, whenever we got this peak there. So in summary, we've defined a frequency response. It's a plot of the transfer function versus frequency. In particular, we're looking at the magnitude and the angle. We can use it to determine the steady-state sinusoidal response of a circuit at different frequencies. And the whole point of the transfer function, the frequency response, is to understand how the circuit processes signals of different frequencies. Does it attenuate frequencies in certain ranges, or does it amplify signals or make them larger? Like that last case with the resonant peak, we had the output greater than the input. If we take a look at the transfer function and plot it versus, in other words, look at the frequency plots, we can understand what's going on. Is it amplifying or is it attenuating? And if so, in what frequency range? So this ends our series of lessons that are review. And in the next module, we will start the regular electronics part. Thank you.